Hey Calc students, this is a video on particle motion. So I'm going to kind of formalize for you what we started exploring in class, which is this idea of a position or a distance function. I'm going to call it the position function here. And this is kind of telling us where a particle or object is along a straight line. And typically we use s of t to be this function. Sometimes it'll talk about like a function moving along the x-axis, and we'll call it x of t, where x is the output and t is the input, because this is a function of time. So after we think about position, we also have this idea of the velocity function. The velocity function is going to be the rate of change of the position. So how fast and in what direction is the particle traveling? Typically we call this v of t. And then the last function we'll think about sometimes is the acceleration function. Acceleration function. This is going to be the rate of change of the velocity. So do I have a constant speed? Is it getting fast? Is the velocity increasing? Is the velocity decreasing? So because these are both rates of change, they end up being derivatives, right? So, this is, before I get into that, this is the a of t function. So now, this is a rate of change of this, so it should be its derivative. So we think about this as being s prime of t, the velocity. And then the acceleration is a rate of change of the velocity, so we can think about it as being the derivative of the derivative. So s double prime of t. And so that's going to come in really handy because it means all of the relationships that you guys know about f prime, and f double prime should also be true when we're thinking about particle motion. We're going to kind of think a little bit more now about what it means, like how does the kind of relationships we know translate into particle motion problems. The first thing we're going to look at is one of the graphs from class. This is going to be in 5th period Will and in 8th period Amelia. And I'm just going to do a rough sketch. I'm not even going to label my axes. It looks something like they were going forward at a constant rate, then they slowed down to a stop, and then they were going backwards at a constant rate. So there's like a little curve right there and there to kind of denote the slowing down right before it came to stop. But this was our position function. And then we can think about drawing a velocity function. And actually I'm going to want positive and negative values on my x-axis, or sorry, my y-axis, because I know there's parts where the velocity will be negative when it's going backwards, right? So the idea here would be, well, at first the person was going at kind of a constant speed. So I should have a horizontal, but it's positive, right? So I should have a horizontal positive line to start. But as I approach where they come to a stop, I need to kind of slow down to a velocity of 0. So I'm going to do a steep drop to get down to the velocity of 0. So this place kind of corresponds to this. I don't know how good a job I did. Then there's a period of time where the velocity is 0 because standing still. And then after that, you start to move in the opposite direction. So now our derivative values are negative. So I have to have a negative velocity to move in the opposite direction. So I have a steep kind of increase and then a kind of leveling off to a constant velocity because this looks like a pretty straight line. Okay, so that's just a rough idea of what the velocity graph looks like. And the key thing we're going to think about, right, first of all, is how can we interpret where the velocity is positive, negative, and 0. So I'm going to divide this into 3 sections. So the first section, the velocity is above the x-axis, so it means it's positive. In this middle chunk, the velocity is 0, and then the last chunk, the velocity is negative. And I'm just kind of like label for you what each of those things mean. So I'm going to kind of show you for this first chunk where the velocity is positive, we know So I'm going to write out, I'm going to kind of do a little box right here to kind of correlate to this left section. So we'd say like v of t is greater than 0, right? That's where it's above the x-axis. That means that what's going on with the particle? The particle was moving away from its starting point in a positive direction, so that means it's going forward, it's going to the left, it's going to the right, or it's moving up sometimes, okay? So this is telling us the direction of the particle. Say the particle moves forward or to the right if it's on like a number line, or we could also think about it as going up, okay? And that's for that first section. For this middle section, this is where the velocity is 0. So what is that telling us? That's telling us that the particle is at rest. Or it's standing still. It's another kind of way it's described. And then the last little chunk, where my velocity is less than 0 or negative, that means that what was happening here is moving backwards. So the particle moves backwards or to the left in the negative direction, or if we're going vertically, down. Okay, so now that we kind of have the kind of visual representations of interpreting what's going on in the position function and the velocity function, we're going to skip the acceleration function for now, but we're going to still think about that in a little bit. So now I want to see, how does this work if I give you an equation? So suppose I have an example problem where a particle along a line is modeled by some equation. So I'm going to call it, actually I'm going to use x, just to kind of see that. X of t, and then my inputs are t. So 2t to the third minus 3t squared minus 12t, where t is time in seconds, and x of t is going to be a position in, say, feet. Okay, so if I say, can we describe when is the particle moving forward, backwards, and at rest? Okay, so how can I decide where the particle moves forward, backwards, or is at rest? Well, I can think about where the velocity is either positive, negative, or 0, right? So essentially what I need to do is use the first derivative test. So let me kind of record what I just said. So we say, when is the particle moving forward, backward, or at rest? Question mark. And the idea is we're going to use the first derivative test. So I'm going to find the velocity function, which I know is just the derivative of the position function, which is 6t squared minus 6t minus 12. I need to find the zeros here. Factor out a 6. Then I can factor that into t minus 2 and t plus 1. So I get t equals 2 and t equals negative 1. Sorry about that. And the one thing I forgot to say is let's assume that t is greater than or equal to 0, that we're only counting positive time. Okay, so in that case, I'm actually not going to include the time of negative 1. I'm going to focus on the time of 2. And so I'm going to put 0 on here, and I'm going to put 2 on here. 0 is kind of like my hard boundary point, but 2, I need to think about what if the velocity is positive, negative on either side of that. So between 0 and 2, if I plug in 1, I'm going to get negative here and positive here and positive that. So I have something negative, which means the function is decreasing. And then if I plug in 3, I get something positive, positive. So I know it's increasing. I also know I have a minimum there, but that is, I don't really care. I do know that what's going on at 2 is that my velocity is 0, right? So that's actually telling me where my particle is at rest. And it may not make sense, but it's kind of like at rest for an instant before changing direction, okay? So our conclusions then would be it's moving forward between, we'll say, starting at 0 and going until 2. Oh, sorry, that's backwards, my bad. Backward, and then it's moving forward for t values between, or just t greater than 2, and then it's at rest at t equal to 2. So notice 2 is not included in any of those intervals because at 2 it's not moving forward or backwards, the velocity is 0. Excuse me. Okay. One more thing to discuss, and that is speed. So I'm going to go on to my next page. So speed is similar to velocity, except it doesn't account for direction. So we think of it as the absolute value of the velocity. So how fast a particle moves, no direction. And if we kind of revisit the activity from class and we kind of think about, I'm just going to quickly resketch something like that. If this was our position function, and I wanted to ask, like, where am I slowing down? Or where is the particle slowing down, and where is the particle speeding up? So if you notice, we know it's not moving at all in this flat part, right? But to get from a velocity where you're kind of moving at a steady rate and then going into, oh, actually, yeah, I will talk about this. Okay, so sorry. So we have like a steady rate of the velocity, but we have to slow down to get to 0, right? And how does this look on the velocity graph? So the velocity graph looked like, roughly like that. So the idea is I'm moving at a constant rate here, so I'm not speeding up or slowing down, really. But when I start this decrease, that's where I'm slowing down, because my velocity values are getting closer and closer to 0, so that must mean slowing down, right? Then I'm at 0, but then I start moving in the negative direction, but I'm actually speeding up here, right? So it's this idea that when my velocity graph is getting closer to the x-axis, or the t-axis in this case, I must be slowing down. When I'm moving away, my velocity values are getting greater, kind of the absolute value of them is getting greater. That must be speeding up. So visually, we're going to kind of cue slowing down with v of t moving toward the t-axis, or the x-axis, and then speeding up as v of t moving away from the t-axis. And if you didn't think about it graphically, but instead we had, say, like a number line with the positive and negative symbols for the velocity and the acceleration, so we did kind of like a curve sketching number line. The idea is that when acceleration and velocity have the same sign, they're either both positive or both negative, we must be speeding up because those forces are moving in the same direction. So we'll see speeding up is when either a of t and v of t are both greater than 0 or both less than 0. So they have the same sign. And then it must be slowing down if the acceleration is moving in the opposite direction from the velocity. So that must mean that you're getting smaller speed numbers, because the absolute value must be decreasing. So then I would have v of t say positive, a of t would be negative, or if v of t was negative, a of t would have to be positive. So this is where they have different signs. Okay, so that's kind of like, now that I kind of explained speeding up and slowing down to you, let's go back to our example equation and see how it applies there. This is the last thing we'll do, I promise. No, you try. So the equation we were working with was x of t equals 2t to the third minus 3t squared minus 12t. Then we found v of t, which was 6t squared minus 6t minus 12. So then now, the idea of knowing if the signs are the same or different for a of t and v of t is that I'd actually need to find a of t and do the second derivative test, essentially. So if I take the second derivative, I get 12t minus 6. I set that equal to 0. I'm going to get, add 6 over, divide by 12. I get 1/2 for t. So now I'm going to kind of combine that with the work I already did in the previous number line. So in the previous number line from the earlier part of the example, we knew that we started at 0. 2 was a critical point for the first derivative, and now I'm going to add in the 1/2 for the second derivative. So we have a of t, we have v of t, and we can also have s of t on here. So v of t, when we did the first derivative test, v of t was negative before 2. So all this was negative, and then positive after 2. And now I'm going to do the same thing for 1/2 with a of t. So if I plug in, I can plug in 0. That's fine, because as long as it's something to the left of 1/2, I'll get this whole interval. So I plug in 0, I get negative 6. So I know that's negative. Then if I plug in something to the right of 1/2, like 1, I get something positive. And since that 1/2 is the only critical point, I know it's also positive on the other side of 2. So now I'm just checking here, and I can see like the signs match between 0 and 1/2. And between 2 and infinity. So that must be where it's speeding up. And then slowing down would be this middle section where the signs don't match. Okay, so that concludes your notes. You're going to be practicing this in class. I may or may not be there. See how I'm feeling tomorrow.